Okay, this is the last part of the chapter 1. So we're on 1.6, which is dimensional analysis. Dimensional analysis is essentially a method to convert one thing into another. And if you can do this method, you're going to be able to do like 75% of the problems in this class. It's really just a unit analysis. So if you keep track of your units, you should be able to solve any problem. So this is called dimensional analysis. Essentially, the definition is using units to problem solve. Okay, all of your units should cancel out. All units should cancel in the end. What that means is you're going to end up in the unit that you want, the question is asking for. So I'm going to show you how to do this. Essentially, we're using any type of equalities. So all of these down here are equalities. These are how to convert from one thing into another, right? You're going to go to Google and type in how many ounces are in a pound. Well, I'm going to show you how to do that math because you're not going to have Google with you on the test or when you're trying to convert something in the lab. So your measured equalities can be turned into what are called conversion factors. Okay, so these are like definitions. Okay, so definitions and conversions for units. Okay, like these here. Okay, you're never going to have to memorize these. I will always give you ones that you need in order to do a conversion, but you're going to have to show me the work on how you get from point A to point B. All right. So essentially what we're doing is we're going to take these conversion factors here and we're going to write them as ratios, okay, because they're equal, right? So essentially if I write, let's use the week and days one, 1 week over 7 days, okay, that's a ratio, right? But those are exactly the same thing. So if I multiply something by this ratio, I'm really multiplying it by 1 because these are the same thing. So this is why this whole thing works. So I can write it this way, or I can write it this way. 7 days is the same thing as 1 week. Okay, they mean the same thing. I can just pick whichever one I need in order to get my math to work out and my units to work out. So you're going to see how I'm going to do that. I'm going to do another one really quick. I got 1 mile is 5,280 feet. Again, not something you have to have memorized, but something we will use. Okay, so 1 mile is 5,280 feet. Or I can write it as 5,280 feet is the same thing as 1 mile. And then we're going to use these in our math. Oh, I actually meant to write these down here, so we're going to flip flop. Okay. What did I want you to write up there? Like, what does this mean? Essentially, what you're doing is you're writing as a numerator over a denominator, just like a fraction. And you are going to make your units cancel out because, right, if you have something on top and something on bottom of a fraction, the units are going to cancel out, or the numbers would cancel out if they were numbers. Okay, so I'm going to show you what I mean. There's some steps to solving any of these problems, but once you guys get this down, it's very systematic and it will work for you every single time. So the first thing I want you to do is always start with whatever your given number is in the problem over an implied 1. So I'm going to do this example right here, 65 inches converted to centimeters. So when I say start with your given, that means whatever number I gave you in the problem, I'm going to start with 65 inches over 1, an implied 1, because you can put anything over 1, right? And what we're going to do is we're going to multiply it by a conversion factor. Okay, so we're going to write an equality as a ratio. So we're multiplying by this fraction, whatever I want to put in here. Now, to decide what to put in here and which thing I want on top and on bottom, essentially your denominator needs to have the same unit as your previous numerator. So if I had inches here, that means I need inches down here. Okay, and I'm trying to go to centimeters, so I'm going to put centimeters up here. So I want the conversion between inches and centimeters. So if you scroll up here, 1 inch is 2.54 centimeters. So that's the one I'm going to use. So I can write it this way. 1 inch is 2.54 centimeters. And that's essentially all I'm going to do to get this conversion. So the way that the units work, right? If I have 1 on top of a fraction, pretend this is one giant fraction, and 1 on bottom, these are going to cancel out. and then I am left with just a unit of centimeters. And if I'm left with the correct unit, that means that you set it up correctly. So all you need to do now is 65 times 2.54 over 1, and that will give you your answer. And the answer to this is not something I did yet. Okay, so the answer to this, my calculator gives me 165.1 centimeters. Now, Sig Figs, okay, we're going to practice with our significant figures. Whatever I gave you in the problem, you should have the same number of significant figures in your answer. So there's only 2 up here, so I'm actually going to round this. That would mean I'm rounding right here. So I would get 1, the 6 would round up to a 7, but I need a 0 in order to get the correct number. So 165.1 would round to 170 centimeters. Okay, now you can do this multiple times. You can do multiple conversions in a row. You can set up as many conversion factors as you need to based on your knowledge in order to get there. So I've got 45 pints. I want to go to liters. So I got 45 pints. Now, I have no idea how many pints are in a liter. I do, however, know how many pints are in a gallon. So I'm going to use that conversion first. There are 4 pints in 1 gallon. And I actually also know the gallons to liters conversion off the top of my head, just randomly. I know that 1 gallon, notice I'm putting gallon on bottom, because gallon's on top over here, is 3.785 liters. Okay, so the reason I did this, my pints will cancel out. Okay, so I put it this way, my conversion factor this way, so that my pints cancel out. And then I have gallons, so I added another one, and I put gallons on the bottom, because those will cancel out. And now I am left with liters as my only unit, which is what the question is asking for. So you can go in any order with multiplication and division. You could multiply all your numbers on top. So 45 times 3.785 divided by 4, or you could go from left to right. You could do 45 times 1/4 or divided by 4, and then times 3.785 liters. Anyway, you're gonna get the correct answer, which is 43 liters. And yes, I did round to significant figures because that's what I gave you in the problem. Okay, so another type of conversion that gets a little bit more complicated is when you have like ratio units, for example, miles per hour. Okay, and if you have a ratio unit like this, essentially instead of writing it like miles/hour, you should write it miles, however it is, however many miles per 1 hour. Put hour on the bottom. Now, remember before, the only time I said you're going to write something on the bottom is if you have a unit like this. It should always still be a 1 on the bottom, but you want to split your unit up in order to convert it. Okay, so if we're converting something like this, you have to make sure that your numerator and your denominator work out the way you want to. So I'm going to convert 34 miles per hour into meters per second. Okay, so I'm still going to follow my steps. Always start with the number I gave you in the problem. So 34 miles per 1 hour. Okay, remember I said write it this way so that you can get your units to work out. So I'm just going to go 1 unit at a time. I'm going to turn my miles into meters. Okay, so I'm going to multiply by some type of conversion factor. I don't know the conversion for meters to miles. Actually, no, I did. I looked it up. So you could look it up if you wanted to, or you could go to feet and then centimeters or whatever you want to, depending on what you know. I will give you the needed conversions, remember. But I looked it up, and 1 mile is the same as 1609.34 meters. Okay, so look at that. My miles have gone away. Now, if I stopped here, I would get meters per hour. But that's not what the question is asking. It's asking for seconds. So I need to do another conversion factor to get rid of my hours. Now, hours is on the denominator over here. So if I wanted to cancel out, I actually had to put hours on my numerator over here. And I know that there are 3,600 seconds in 1 hour. Okay, so now my hours will cancel out and I'm left with meters per second. Okay, and you can do this in any order. It doesn't matter because it's all multiplication and division. So now I'm going to do 34 times 1609.34 divided by 3,600. And I get that this is 15 meters per second. All right. Okay. You might want to try a couple more of those. There will be definitely some in the homework. If you need help using Chem 101 and how to drag and drop those dimensional analysis things, please let me know. Come see me during my Zoom. All right. Let's see. Example number 10. A chemist wants to measure out 0.214 milliliters of benzene, but lacks the equipment to accurately measure such a small volume. chemist, however, is equipped with an analytical balance capable of measuring 2.001 grams. Looking in a reference table, the chemist learns the density of benzene is this. How many grams of benzene should the chemist use? Okay, well, this is kind of a density problem, and we'll talk about density here in a little bit. But essentially, I got a lot of numbers here, so you got to decide which one to start with. This is just describing the balance. So this plus or minus 0.0001 grams, you can ignore that, okay? What I have is this ratio here, okay, which is its density, and this volume here. Okay, so my tip for you is always start with a volume or a mass if you can. I don't want to convert this density unless I'm actually trying to convert the density. So if you have the option, try not to start with the ratio, try to start with a different unit. So actually, I'm going to start this one, 0.214 milliliters. Oops. Okay, over 1. All right, I want my milliliters to go away. Now I'm not trying to go from like milliliters to liters or anything. I actually want to know how much stuff to weigh. So I can use this density with this ratio as a conversion factor, because what that density is actually saying is it's 0.8765 grams per every 1 milliliter. So my milliliters will cancel out. This will give me the grams that I should mass, and I get 0.188 grams of benzene. Okay, so that's like one type of problem that you can solve using conventional analysis. Now, sometimes you might run into units raised to a power, like square inches to square centimeters, or cubics, and you need to be really careful with those, because I know, yes, that 1 inch is 2.54 centimeters, but 1 cubic or square inch is not 2.54 square centimeters. They're not the same thing. If you actually want to turn this into a conversion, you have to square 1 squared, inches squared, equals 2.54 squared centimeters squared. So you also have to square the number, okay? So keep that in mind when you're trying to do a conversion like this. So I'm going to right here. The conversion numbers must also be raised to a power. All right, so if it's cubic, you need to cube the number. All right, so I'm going to do this example right here. I'm going to convert 0.196 square miles into square yards, okay, based on what I know. So I'm going to start with my number. Square miles would be square miles over 1. Okay, now I want to go to square yards. Now, I don't actually know how many yards are in a mile. I do know how many feet are in a mile, and then how many feet are in a yard. So I'm actually going to go to feet first. So I want miles squared to turn into feet squared. Now I know that there are 5,280 feet in 1 mile, but in a squared one, there are 5,280 square feet in a square mile. Okay, now I can do the same thing with feet to yards. Square feet to square yards. Yards squared. I know that there are 3 feet in a yard, so there are 3 squared feet in a square yard, and now I can do my math, right? All my units cancel out. Square miles, square feet, and I'm left with square yards. Now, 1 squared is just 1, so you can ignore those. So I'm just going to do 0.196 times 5,280 squared divided by 9, which is 3 squared, right? And I would get, and I'm going to round, 607,000 square yards. So give that a try on your calculator. I rounded to 3 Sig Figs. That's how many was in the problem I gave you. All right, last thing we're going to talk about in this unit is density and how to solve density problems. So your first lab is going to be on density. Density is something that is measured, that is defined for every single substance. Every single substance has its own density. And remember, this is an extrinsic property, so it doesn't change with the amount. So now, no matter how much water you have, its density is always 1.00 grams per cubic centimeter or grams per milliliter, no matter what. Okay, well, as long as you're at 4 degrees Celsius. But things have defined densities, and we can actually identify things based on their density because of that. So it can be really useful. Okay, so what is density? It is the mass per unit volume of a substance. The equation is d equals M over V. Okay, that's an important one to know and remember. All right, mass is almost always measured in grams, and volume is almost always measured in cubic centimeters or milliliters. Okay, so your units are usually going to be grams per milliliter or grams per cubic centimeter. Now, I do want to point out something that's going to be really useful to know here. 1 milliliter is the exact same thing as a cubic centimeter. These convert from one to the other. And so whether you're using a liquid or solid or something, that's going to be a really useful equation to know that those two things are equal. All right. So we're going to do this example here. Give it a pause, try it on your own, and then check your answer. What I'm going to start with, I have two numbers. It says, what is the density of this 15.5 gram sample that occupies 16.7 milliliters? So you need to be able to tell, I'm not going to say the mass is blank, the volume is blank. You should know by looking at the units, grams and milliliters, that this is going to be a mass and this is going to be a volume. So the density for this is simply 15.5 grams over 6.7 milliliters. And that means its density is 2.3 grams per milliliter. Okay, and if I had a table of more densities, I could identify what that object was. Okay, so in a lab, you are going to have to measure density. So that means you have to measure mass and you have to measure volume. Now, mass, we just measure on a scale. You're going to have a balance, an electronic balance. So when you're writing procedures or answering questions, that specific piece of equipment is called an electronic balance. Okay, and then for volume, there's a couple ways you can do it. If it is a regular shaped object, you can use the equation, right? Block is length times width times height. And a cylinder is pi r squared h. And a sphere is 4/3 pi r cubed. I don't expect you to memorize those. I will give them to you if you need them. But if you can measure those, then you can figure out what the volume is. Okay. Now, if it's an irregular shaped object, you are going to use what's called water displacement. Okay, you just read wherever your water is starting at. This one started at 50 milliliters. You drop your object in and then you read where it ends at. This one's 75 milliliters, and then you subtract whatever the difference was is the volume of your object. So essentially the equation, if you want to write it down, is the volume final minus the volume initial equals the volume of your object. Okay, so anytime you have an irregular shaped object, you should do water displacement. Okay, so now how do we do these problems where you have to solve for mass or volume, which you will absolutely be asked to do? I have an example here, and I'm going to do it with two methods. All right, so what volume would a piece of aluminum with a mass of, let's see, I've got 254 grams occupy if I gave you the density as 2.70 grams per milliliter? So algebraically, I noticed that the word density is in here, and I know that the equation for density is D equals M over V. Okay, so I'm going to plug in what I know from the problem. I know the density is 2.70 grams per milliliter. I know the mass is 254 grams, and the question is asking for the volume. So that's my unknown. So you could algebraically determine this. You could do cross multiplication or move the V over or whatever, and you should get that V is 94.1 milliliters. Now you can also do dimensional analysis, the method that we've been talking about today. You start with your mass. Okay, remember I said to start with a mass or a volume. Something that's not a ratio unit would be great. So I would start with 254 grams over 1. And then I can use my density as a conversion factor down here because I know that there are 2.70 grams for every 1 milliliter. Now, in this case, I need grams to go away. So I'm going to put the grams part, the 2.70 grams on the bottom and the 1 milliliter on top. Because remember, you can put it whichever way you need to in order to get your units to cancel out. So my grams will cancel out, and this will tell me my milliliters. I would also get 94.1 milliliters. Either method is completely acceptable. All right, last example, find the density of an unknown liquid in a beaker. Okay, so this is something that you could potentially do in the lab. It says the beaker's mass is 165 grams. when there's no liquid present. Okay, so you can't just put liquid onto a balance, right? You have to put it in something. So what I'm going to do is I'm going to mass this empty beaker, and then the beaker with the liquid is 309 grams. So this is kind of like a volume displacement thing, but instead this is mass. So in order to figure out what just the liquid is, that's pretty easy. I can do 309 grams minus 165 grams. And I'm going to get that the mass of just the liquid is 144. Okay. I also gave you the volume, so maybe I put this into, it's in a beaker, so you can read 125 milliliters on there. So I have a mass, I have a volume. Now I can do my density is 144 grams over 125 milliliters. And so the density of this is 1.15 grams per milliliter. Then I could reference a table and be like, oh, what's a liquid that has 1.15 grams per milliliter? And you can identify what that liquid is that way.